So let's have a look at Docker. And this is basically the Docker container management tool. So what is it? It's basically it's a container platform. It enables you to create containers, run images and things like that. And it's basically each container runs typically one application is the idea. A container can run multiple applications. That is allowed. But the kind of philosophy behind it suggests that every container should contain a single application and have a very, very minimal implementation so that there's no interference between different applications. So, Docker container consists of a base Linux operating system, which is basically all the tools and utilities needed to operate a Linux environment. So you'll have all the tools like ls and ps and the ones that you're going to need. But what you won't have are any of the boot mechanisms, processes or scripts, because there isn't a boot mechanism, and anything else that's required, any packages that are required to operate. And so it's a good jail. You can't get out of it. We don't know of anybody that has got out of one yet. It might be possible. And what we do is we start off with an image, which is just basically a big file, or maybe a not too big file, and then the image becomes the runnable container. And so outside you've got Dockers, you have many containers, you've got the operating system and kernel and anything else. Docker is just an application that runs on your operating system and enables you to run containers seamlessly as standalone applications, which are completely isolated from anything else. So Docker is traditionally Linux. It was for a long time, it was only supported on Linux until fairly recently, because it needs the functionality from certain versions of the kernel, which is anyone after the technology was enabled. It requires a 64-bit installation and at least a 310 Linux kernel. And it'll run on most flavors of Linux, not necessarily easily on all of them. For the popular ones such as Debian and CentOS and Ubuntu, it's pretty easy to get it running. Though there are some issues with the CentOS version. I found some problems. And you can get it as an RPM or an apt package and just install it, or you can download from Docker directly as a binary version. For some versions of Linux, you need to do that, use a binary version. If you go to the Docker website, it'll tell you what you need to do for your particular flavor of Linux. Docker for OS X came out fairly recently. It was earlier this year. It now runs natively on OS X, which is good. And you just get a DMG package, which you just install it. It's built on a hypervisor technology. It only works on fairly recent Macs. So it's got to be at least a Mac 2010 because it needs the support for the memory management within the CPU. And earlier Macs didn't have sufficiently late versions of the processor that would supported this technology. It requires a fairly recent version of OS X, 10.10.3, and at least 4 gigs of RAM because it does use up some memory. There is a problem with the OS X version, which was very frustrating when I was working on this material. There has been a problem that Apple and the Docker people have got an issue communicating about networking. So when you install Docker on OS X, which is what I'm actually running it on, you can't do proper networking because Docker is not capable of creating the right network device to be able to communicate externally. It's not the end of the world. You can still use Docker on OS X, but you can't do certain things where you've got containers spread over multiple hosts. There's also a version for Windows. It only works on the very latest versions of Windows 10, though they said they might support earlier ones. It also requires a package called Hyper-V, which is a virtualization package to work. And it does the things and virtualizes the environment so that you can run effectively Linux stuff on Windows. So it has to effectively look like a Linux kernel in some respects. VirtualBox for virtual machines cannot be run at the same time as Docker because the Hyper-V package and the VirtualBox application are incompatible with each other. They can't work together. So if your OS is not supported, there's a thing called Docker Toolbox. And Docker Toolbox is what you had to use on OS X and Windows before the first part of this year when it was finally released. What it is, it's a virtual machine. It uses VirtualBox and it's completely packaged, a virtual machine running a Linux operating system which has got Docker installed on it. And so you just run that as a normal virtual machine on your operating system, and then you've got Docker which can then run other applications. Docker Engine is the key part. So Docker has got a number of components, as we'll be seeing, mainly today, but there's another section on another aspect of Docker in a later lesson. It's client-server. You've got basically a background daemon process which does all the work, and it's got a RESTful API. This normally by default works over a Unix socket, so it requires the API, the client program, to run on the same machine if you've got it on the Unix socket. It is possible to make it listen on a TCP IP port, and then you can have remote clients to the Docker server. This is one area where you can't work on OS X because if the server's on OS X, the client can't connect to it from another machine. But you can go the other way. So the server is the Docker daemon, and what it does is it manages the containers. So it can go and fetch them, it can build them, it can run them, and it can put them somewhere else. So the containers themselves, where are they stored? Well, there's a number of places. Docker Hub is a repository, a set of repositories up on the cloud, and that enables you to get images of a vast number of things. There are Docker images for all of the major distributions of Linux, and they've got multiple versions of each of the distributions of Linux. They're all cut down. It's also got many, many applications. So if you want, say, a MySQL server, there's a container up on Docker Hub which has got MySQL running on top of some flavor of Linux, and you can just pull it down and run it. And any other application which is popular. So if you want a Jenkins CI server, continuous integration server, you can just pull one down so you don't have to configure your own. And these things are pretty neat actually, because what they're configured in such a way that if you specify certain options when you run the image as a container, it will effectively configure itself. So as we'll see in the next lesson, if you pull the MySQL container down, you can fire it up in a way that it creates a database and a user. And then you can also fire it up when it's been configured and it's got an existing database and users. And you can also fire it up as a client and access another container, which is the database server. So they've done quite a lot of work on making this stuff really user-friendly. You can also have private images. You can create your own images. And in fact, Docker keeps its own collection of images locally, so it doesn't have to go fetch them all the time. And there are other places where you can get images from other vendors. So an image is a template, and say it's usually a cut-down version of a Linux operating system, and you just add applications to the image. And basically an image is a template, and then you provide a set of operations which builds on it. So you just say, okay, I want to add this, install this software, I want to do this, do this, do this. And it basically adds layers to the container. And then you've got your fill image, which can then be run. They can have all sorts of things. You can run them, start them, stop them, delete them. They're all good stuff. So the images are built in layers. Each is a file system. It's a union file system. So what will happen is, if you go to Docker Hub and pull, say, a MySQL image, you will see it'll do a series of downloads, probably about maybe 6 to 10 separate downloads. Each of the downloads is a separate layer on top of the container. Does it support HTTPS? Yes, it does. You might need to do some configuration for configuring HTTPS, but yes, it does. One thing we will be doing actually is building a container which is an SSH server, so we can connect via SSH to it. So yeah, it pulls the base image, it pulls the layers, and it does the downloads in parallel. And then when they're all there, it just builds it all together into the base image as a single, what looks like a single unit, but it's actually layered. And so if you do one thing that's very powerful is if you make a slight change, it won't have to download everything, or if something slightly changes. So to give an example, I was trying to build an image, and as inevitably I made some mistakes in the configuration when I was trying to build it. And so when I made changes to my configuration and did a rebuild, it didn't have to go and fetch the bits it had already got. It had cached them effectively. So that meant the actual bandwidth and download that was required was minimized. It only downloaded the things that I'd added which hadn't already been done, which is really neat. So you have an image, and you use the docker run command, which creates a container. So basically the image is read-only, effectively, and the container is a copy of the image, which is an actual container running the file system. So when you say run, it'll first of all look for a local copy. If it doesn't find it, it'll go and search for it. And the container is created from the image itself, effectively as a separate file system. It adds a write layer to it at the top of the file system so that you can make changes to it. It also creates a network interface and assigns it an IP address. The way it actually works is the Docker daemon acts as a gateway to a private internal network on your machine. It's an internal subnet, and the containers are attached to that subnet. But we'll look at networking in more detail later. It's actually quite powerful. You can also connect optionally the input, output, and error streams, so you can interact with the container if you wish, or you can run it as a background process. So the Docker, whenever it's run, the Docker container just appears as a child process. So this shows the daemon process here, which started with certain options, and then process 1410 is a child of Docker, which is the container running, in this case, a shell, which is one way of actually starting containers and quite powerful. So to run an image, it has to be on the computer, and so Docker has its own little collection of images, and if it hasn't got one, it'll either need to be created locally or pulled from a registry. And the pull just simply does a transfer of all the layers and puts them together into a cache, and then you run them to get the container. So this is the example that's shown there. We wanted CentOS. Every single container usually has a :latest version. You can specifically ask for a version, so you can say I want CentOS version 7 point something, and it will fetch you that particular version of CentOS. And then you can run that container. And what you do is, the container will have some kind of default program which is configured into it, which it'll run. So if you just run it as a background process, it'll fire up some application which the container was built to do, whatever that might be. You can, in the case of, say, a CentOS one, or any of the containers, you can specify a command. So if you go docker run CentOS :latest who am I, it'll create a container from the image, start it up, and run the who am I program, and it'll then exit. And the same with any other command. So you can run a single command like this. Not tremendously useful, but it shows you the principle. Typically, you'll be running a real application, or quite often you'll run a shell so that you can interact with the container itself and make changes to it. So the way to do this is to run it interactively. Docker run -I keeps the standard input stream open, so you can use the keyboard, and -T allocates a TTY device, which means you can actually interact with the TTY drivers inside the container. And you normally go docker run -IT or -TI, specify the image, and specify the path to a shell. And that will actually run that CentOS container and give you a shell prompt. So you get the hash prompt as a root shell. Incidentally, the processes inside the container, your bash shell will be process number 1 inside the container, because the process IDs are mapped. So process ID 1 in the container will map to process ID something else in the actual host operating system. You can do some interrogation. If you do a docker ps, it'll list all the running containers in your machine. and the container will be given a name. By default, the name is quite comical, but you can specify an actual name. You can also do Docker stats, which shows you the resource usage, and you need to terminate that with a Control-C. So it's something to try playing around with. So it's very useful. I always do this. Docker run -it -- name, and then give it a sensible name, because then you can use that name to control the container. So that's the first one's running the container. You can stop it using docker stop, and you can remove it. Docker rm deletes the container itself, which you probably want to do quite a lot of the time because you just throw it away. We'll talk about external file systems and what happens, because when the container is destroyed, everything that goes with it goes as well, unless you've attached some external storage, which we'll look at. You can also attach to a running container. So, for example, if you're running one container interactively, like the first one, if you go to a second terminal and go docker attach CentOS, it'll attach your terminal to it, but you actually got the same session. So if you type into it in one terminal, you'll see the output in both, because it's effectively both attached to the same container. And there's this magic keystroke Control-P, Control-Q to detach from the container, leaving it running. So that means you can effectively walk away from detach yourself from the container and then reattach yourself later on, if you wish to. There's docker stop for terminating containers. You can optionally give it a time interval, and say main process ID 1, which is not in it. It's the main application started in the container, gets a term signal, and then after the interval it will get a kill signal to make sure it goes away. You can pause the container as well. That basically puts all of the processes in the container to sleep. It doesn't use the standard Unix sig term mechanism because of the process fillers. You might be able to see them. It uses a control group freeze mechanism, which basically all the processes in the C group and its child groups are put to sleep without the processes knowing about it, and then you can resume them if you wish to with the unpause. When a container terminates, it actually doesn't go away. It just goes into a stop state. If you do docker ps -a, it'll show you all of the containers, including the stopped ones, which is very useful. And you can restart it by doing a docker start, and you've got the option of connecting the input and output streams to it. Removing containers, you just do docker rm CentOS in that case. If the container's running, it will refuse to do it unless you add the -f switch to force it to stop. ps -aq command shows just the container IDs. So that command at the bottom, docker rm $docker ps -aq, effectively deletes all the containers on the current machine. You can run them in the background by using the -d for daemon switch or detach switch, and you can send signals to the container as well using the docker kill command. Right. So that's the idea of Docker containers. Now Randy will demonstrate how to use the Docker command to find and run Docker containers.
Welcome to DevOps Lesson 2, Lab Number 1, Docker. Let's switch to our terminal. And the first thing we want to do is to make sure that we're running the latest version of Docker. So we can get that information by saying docker -- version. And there we see it's release 1.12.3, which is just fine for us. Next, we want to get an image that we can run as a container. There is a public registry that's available by default, and I happen to know that there is a Linux distribution that we can use called Alpine. So we're going to pull that image down from the registry and load it on our machine in a local cache. There we go. It's pulled down. Now we can run Docker images to see what's on our computer. And there we see that we have the latest version of Alpine, and here is its image ID. The image ID is a hash of the contents of the image. And you can tell if an image is the same image as another one on your computer by comparing the image IDs. If that's the same, then you know you have the same image. That becomes significant because sometimes images have multiple tags and they'll appear as different lines in your list, but you can see that they all have the same image ID, so you know they're aliases. Now look at the size. This is less than 4 megabytes in size, which is remarkable for a Linux distribution. Now let's run this. We'll clear the screen and we'll say Docker run, and we want a TTY or terminal interface and connect to the input-output streams of the container. We're going to give the container a name. We're going to call it client. That's the name of the container that's running. Remember, the image is different. The container comes to life, puts a read-write layer on top of the image, and then allows us to continue on, run a program or whatever we need to do. So we'll say that we want to run the Alpine image, and when it comes to life, specifically we want to run the program bin sh, which is the Alpine shell. So let's do that, and notice how quickly it comes to life. That's one of the benefits of these containers. That comes to life in order of milliseconds, whereas a virtual machine can take a minute or 2 minutes to come to life. And this is Linux, so let's check. I can say date, I get the date back. I can say present working directory, we're at the root, and I can ask who am I? And it comes back and says you're root. Okay, well let's cd, which takes us to the home directory of the current user, and we see that it's /root, which is correct. And now we want to touch a file, and that's going to make an entry in the file system. So if we do that and say lsl, we see that we have the file. It's 0 bytes long because we didn't add anything, and we've created state. So let's exit and clear the screen. Now there is a docker ps command that looks at the process status, and there's nothing running. But if we say docker ps-a, we see that we have our container. It's named client. It's based on the image Alpine. The container has its own identifier, and it was running the bin sh command. But it stopped. So we want to restart it. So we can say docker restart client. Now if we say docker ps, we can see that it is up and running. However, we're not attached to it. So let's change that. Let's say docker attach client. And now we're back connected to that container. If we cd to the root directory, confirming we're there, and then we say ls-l, notice that our file is there. So we have rejoined that running container, and we can see that the state that we created is still there. So let's look at a counter example. Let's go back up to the command that we used to create that container, and this time create one called client2. And if we go to the root directory, let's confirm that's where we are, and list the directory, we see nothing. So let's go outside and take a look at docker ps-a and see what's going on. We have two containers. Notice the names are different. There's client and client2, and they were created at different times, run at different times, but they're running the same program. So we've got two different sets of state based on the running of the Alpine image. Okay, now let's remove these containers. So we're going to say docker rm client and docker rm client2. And then we're going to say docker rm client2. And now if we say docker ps-a, we find that there's nothing there. Okay, let's pull down another image. We're going to say docker pull the requisite hello world. And now we can see, let's type that correctly, we have images. So we still have the Alpine image, we only removed the containers, and we now have the hello world image. So we can say docker run hello world, and it comes back with an output message. So this is a case where there is a default program that runs. All we had to say is run the container. It pulls it into memory, activates the container, it jumps to the default running program, and then displays this output. And let's clear the screen and look at the images again. Notice how small these are. It's a handcrafted image. that only requires 1.8 kilobytes. Truly tiny. Okay, so now let's clean up after us. What we want to do is run the docker rm command to remove containers. And what we're going to do is use docker ps-aq as a command to return all the identifiers of the containers. And there is one. That was the hello world container. So what we're going to do is we're going to say docker remove, and we're going to spawn a child process, and that's going to run the docker ps-aq. It'll return those numbers, and then we're going to remove all of them. So there it is. And there's equivalent command for images. You say RMI, and we're going to say docker images -q for just their identifiers, and that will remove all of the images. So if we clear the screen, say docker images, we see that there's nothing on our computer.
Hey, want to become an expert in cloud computing? Then subscribe to Simplilearn's channel and click here to watch more such videos. To nerd up and get certified in cloud computing, click here.